Hello everyone and welcome into yet another live stream. That was quite a delay, but here I am. And today, well, you obviously know, because of the title, you obviously know what it is today, it's Science Friday! Yeah, it's Science Friday, the series on the channel in which we do science because it's Friday because we do science on Friday. It's a long series on the channel. Anyway, welcome to daily charity checkup day 60. My goodness, it's been 2 months. That's 60 days. Wow, it's a lot. It's a lot of days to stream daily. Anyway, today we will be. Is the stream public? It is. Great. Today we will be walking on the hyper operational math, obviously. Yes. But how? I am so glad that no one asked. Let me just there we go. Is the stream set up? I think so. Here's the thing. I just have all of the stuffs open. But here's the thing. I have two things for today. Two very interesting, relatively very much interesting things which I would like to share with you. First of all, paint. I have my graphical tablet, so I'll have to draw with my mouse, so it will look terrible. So, paint. Here's the thing. We already know that a to the power of b is not always equal to b to the power of a. I don't know how to do not always, just not always equal to b to the a, right? We also know that a times b is not always equal to b times a. Now the only thing left to prove is that a plus b is not always equal to b plus a. And wouldn't you know it, I know how to prove it. I know, yeah. Here's how you prove it. It's cool. Great. So, let's imagine we live on a sphere. This is our sphere. It's funky. Yeah, because, I know, I want to just... There we go. Let's imagine we live on a sphere, right? This is a sphere, not a circle. That's important. On that sphere, we can move up, to the side, down, and whatever else you'd like to go. Now take a look at this. If you'd like to move somewhere on the sphere, for example up, then you will end up up. You'll end up over here. So this is the up path. On the other hand, and then if you from the up will move right, then you'll end up, so this, if you'll move up, and if you'll move right, you'll end up over here. But on the other hand, if you move right and then up, then you end up over here. Which means that up plus right is not equal to right plus up. The reason for that is very simple. When you go to the right, well, when you go up, your right is the previous down, so that's the reason. Funky sphere, am I right? Those spheres. Ha 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 ha. So, I'm sorry, I'm I'm excited, okay? So yeah, so addition is not commutative. That's great. That's great news. I mean, it is commutative on all of the complex numbers, and I do mean all of the complex numbers. Is there a name for them? That's a good question. Sequence of algebras over the field of real numbers, twice the dimensions of the previous one. So addition, if I'm not mistaken, works on all of the algebras over the field. All of them. Multiplication works up to complex numbers, and powers don't work at all. Great. Wow. Cool. Great. Amazing. Wonderful. This is exciting because what that means is that not being commutative as an axiom works. It is by definition not commutative. So addition is not commutative. Every case where it is commutative is an exception to the rule. This is a bit different from normal maths. And by bit different, I mean very different, because I'm pretty certain that addition is defined as commutative. It is not. It is not in this case. Now, the second piece of insight is the roots. This will be fun. Roots, right? When you have roots, here's the problem with them roots. When we have, first of all, let's start with logic gates. All right. So, sorry about that. I'm getting kind of sick. Over here, we'll have inputs for logic gates, and over here we'll have the output. That's why usually input output. Fun fact for all of you computer science nerds. Input output, right? Now let's imagine logic gate like AND, for example, because why not? In AND, it looks like this. We have 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1. Because AND returns a 1 only when first and the second one are 1. That's the rule. Great, right? So now, yes, that's how AND returns. But there's a problem. You see, we have 2 inputs and only 1 output. And that is a huge problem. Why? Because that means there is some information loss. Yeah, there is information loss, because if your AND gate returns as 0, I have no idea which one of those that is. And oh boy, this is actually quite familiar. Familiar to what, you may ask? Well, it is obviously familiar to roots. Because you see, when we get... this is familiar to roots because this will return a positive number. Wait, give me a second. I want to phrase that correctly, as if to not make any mistakes, because that would be rather shameful. In this scenario, in this case, making mistakes is obviously all very natural. We're all only human after all. But in this case, I would like to phrase it right the first time to then not correct myself. Oh yeah, multiplication, right. When we have multiplication, right, A times B, then when we have this multiplication, because we have some multiplication with that, this is equal to C, right? But we have 3 possibilities. Let's say that we'll have A, which will be equal to negative B. So A is some number, for example 2, B would be just negative 2. Just no. A is equal to negative B. Now we can do it like this. A times A is equal to C. A times B is equal to negative C. B times A is equal to negative C. B times B is equal to C. Do you see the similarity? We have 2 inputs and only 1 output. which means there is information loss. Based on this, we cannot deduce which case happened. That is a problem for two reasons. First of all, we don't know if we multiply the negative number by negative to get the positive number, and we don't know which way we multiplied them. That's why it's a problem. It's a huge problem. So what we'll need is a way to save that information. Normally in computer science, it is possible to create different kinds of logic gates, some sort of very powerful logic gates with two inputs, two outputs, which basically means that if this is an input, this is an output, then let's do the AND gate again. 0, 0, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0. I don't know if this is the best. It's fine. So for as an output of the logic gate, we'll have 1, 1. Then over here, so basically, yeah, AND is actually very tricky to do. Fudge sticks. Let's do EXO. EXO is simpler to do in this case. EXO, basically, EXO is should be a very simple case. Actually, AND could also work. Basically, the idea is that you have multiple outputs. You have multiple outputs, and then you just use the information gathered from those outputs. But based on these outputs, you can read which input happened. Yeah, it's a neat trick. Anyway, so cool. Now all we need to figure out how to make roots with multiple outputs. Which is, very normal mathematics, right? Alright, so first of all, so music probably. Yes. Time to go back to our original equation, which is this. I still very much like it because this basically creates anti operations on just operation or just hyper operations, which is very convenient. That means we only have to define normal operations. If we define normal operations, then we also get anti operations. The problem is we cannot really define hyper operations yet because we just don't get it. So you have to know whenever the number originates as a positive number or a negative number, which in conventional mathematics is just madness. But fortunately, we are no conventional mathematics, so we can say that numbers contain both value and their original state. Mathematics, so we can try some unconventional methods and see what we get. Now, information loss. The problem of information loss is not really new. It happens everywhere. Coffee? It happens everywhere. Well, not everywhere. It happens every day in our normal day-to-day lives. And I do mean it. If you are reading this, you are probably using some sort of processing unit, which means that you are utilizing logic gates. Yes. Now, inside logic gates, information loss happens all the time. Let's take an AND gate for example. I always get this wrong. Okay, fine. Take an AND gate for example. Now, insert table AND gate like this. Input 1, input 2, output 0, 0, 0. I should color code them. Would feel better. Oh wait, this black. How do you color there we go, gaming. This. No background, none. Great. 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1. Alright, great. First of all, this should be green. This should be red. This red? Absolutely not. This red? Yeah. Come on, just let me. I just want to select this. There we go. These are all the possible inputs and all the possible appropriate outputs for a logic gate. For an and logic gate. Logic gate, and we can observe the information loss in action on the first line. If our output is equal to 0, then there are 3 possible inputs which would work in this scenario. and we have absolutely no idea which one it actually is. Okay, great. Oh boy. Actually, yes. That is in information. Well, I already said that's information. My heart might go offline. I can't even finish a joke right. I should stop. Okay. Wow. And you may think that that this is unrelated math, because exponents are so much different, but it is not. Actually, now I think about this, information loss can happen. Can it? We certainly can get information loss. Oh wait, wait a second. That's actually a light bulb just turned itself on in my head. Here's the thing. I mean, it's not. It won't change everything, but it might prove it a bit nicer. Because here's the thing: when we have a, let's work with real numbers. -7 times -1, that would be equal to 7. And so then, if we divide that 7 by -1, we get back -7, which means times -1 and divided by -1, those are, this looks like a 2, 1 divided by -1, this is an anti-operation to this, right? So it does work with negative numbers fine on other operations, it just breaks with exponents because when it comes to exponents, we don't have a good way to for treating negative numbers, because negative in roots, so root the negative first, that would be x to 1 divided by -1, which is then just reverse it and x to negative first. Here's the problem, when it comes to roots, right? Roots don't follow this pattern. Like this, in order for it to be, valid in hyperoperational math, would have to be equal to this. To the power of b tetrated negative first. What it actually is equal to is, in normal mathematics, is equal to this. X to... how do I know? Well... negative... not negative b, that would be 1 to negative b. No, x to b to -1. Yes, that's what it's actually equal to. Now that's a problem, because what that means is that's an operation with x up arrow, b up arrow negative. And that means that for addition, for example, that would be x plus b plus -1. For multiplication, that would be x times b times -1, which, you know, it's just, it don't make much sense. That's why roots won't work. That's why we need to change the roots for this. The problem with this, though, is that, if I'm not mistaken, if you tetrate something to negative first, you get a 0, which is quite problematic, because that would mean that, like, the hyperroot of any number would be equal to 1. Which is, well, it's not that useful, is it? I wouldn't call that too useful. It's not really that useful. So we need to also change the iteration somehow, because something's up with the iteration 2. Something, a lot of stuff, but it's not. And that's because we can create the exact same table for multiplication. And we will create the exact same table for multiplication. There we go. Now over here we'll have a different. This will be actually, it will be different. It will be a different table. C, A, B, -C, if I may, -C, B, A, -C. I do not follow your reasoning. Listen, don't worry, I do not either. B, B, C. If equation, insert equation, if I may, there we go. If A is equal to -B, try it at some point. Don't fight. Don't try it. A is equal to -B, and C is equal to A times A, then we can clearly see the problem. All right, I have to fix these colors. Then they don't make sense. This should be addition. Because these are positive, these are negative, that's true, and these two also should be negative. There we go. Do you see the problem? There are two possible inputs for C, because that could be either A times A or B times B, which means that we experience information loss. Now, proposed fix for this, as I said before, is madness. It is absolute madness. Because, yeah, I have a fix. It will be insane, though. And not in a good way. But I mean, we could try. This is all still a full experiment, so might as well. No shame in trying. No shame in trying at all. Information loss. Information loss. But what can we do about it? Well, first, in our AND logic gate case. Now this is problematic, because for AND logic gate case, right, I know how it would work with 3 outputs. With 3 outputs, that's piece of cake, because you just take those and assign them to it's a piece of cake. With 2, I am going for 2 outputs, which is worse. Yeah, it's worse. I'm looking forward to try to comprehend this paper when it's done. When it's done, you better believe I will make a video about this. I will make a live stream about this. I will make a series of shorts about this. I will message Grant Sanderson from Free Blue and Brown to make a collab live stream about this. Then after I get rejected, I will message Blackpen Redpen to make a collab live stream about this. Then when I'll get rejected, I'll message the Mathology to make a collab live stream about it. Then when I get rejected, I'll message the number file to make a video about this. Then when I'll get rejected, I will make another video about okay, great. Now now what? Well, now lost my phone. Oh yeah. And logic case, gate case. I also know how to do it when with two things, but it would be worse, objectively worse. Oh, it's not as easy as I thought, honestly. Honestly, it's not as easy as I thought. I thought it would have been easier. Alright. I know how to do the free outputs. With free outputs, as I said, piece of cake, just take those two over here. In order to fix our AND logic gate, all we need to do is just add additional outputs. Yeah, I will do it with 3 additional outputs. It's easy and I'm lazy, so yes. Input 1, input 2, output 1, output 2. Great! Because now all we need to do is just 0, 0, 1, 0, 0, 1, 1, 1. Now the appropriate output, which is 1, 0, 0, 0. And then just copy those over here. That's it. Great, so let me just color code them correctly because it looks nice. I want this to be readable. I mean, I'm not using too much, you know, of actually... I'm not using that much math here. That much, you know, hard math, paper-worthy math, so... That means it won't be a hard read, this entire paper, but still. Yeah, I mean, it works. I mean, it works. It works at this point. There's no information loss. This is the dumbest fix in this case and in this scenario. It is the dumbest fix I could think of, but it works. That's great. I mean, I'm thinking about this like a programmer, and I hate that. As a programmer, in order to fix this information loss, I would just store the information. And I would just have every single number as a vector with all its previous number states saved. But I think that's just my inner programmer telling me that I should, you know, give up mathematics. Because right now what we have, by the way, right now we have created some stuff though. We have the fixed point, we have the half function. Negative is just a negative number, but I write it this way to actually have more clear. The half function is pretty neat. I really like the idea of the half function, of having a different half function for every single operation. This is half point, but half point is just the one, and half function is for every single other different number. Yeah, there it is. Oh, if we'll end up with something that could calculate this, I'll be so happy. Okay, great. So now all we need to do is figure out how to fix roots. How is an engineer with such logic gate adjoint out the outputs 2 and 3. The problem is that if if I wanted to fix that correctly, what I would have to do is I would have to add 1 somewhere over here. If I could do it with 2 outputs, because yes, it is possible. It is obviously possible with 2 outputs, but in order to add with 2 outputs, I would have to add 1 somewhere over here, which would kind of break the meaning of the logic gate. Yeah. We cannot really merge these two together because then we would end up with 0, 1, 0, 1, so there will still be information loss. Because that means if we end up with 0, 1, we have no idea if that was the initial state or if that was the initial state. And we have to distinguish between these two because nothing is commutative anymore, which means that, A to the B is not equal to B to the A, which means that A times B is not equal B times A, which means that A plus B is not equal to B plus A. So in this house of madness, we do need this. If everything was commutative, that would be great. That would be great. Unfortunately, it's not because I messed it. Well, I didn't. I changed the rules for the wars. The one neat thing about this, one really neat thing about the AND gate, right, is that it's multiplication. It is genuinely multiplication. 0 times 0, because 0, 1 times 0 is equal to 0, 0 times 1 is equal to 0, 1 times 1 is equal to 1. That's really neat, which means this could be a solve for multiplication just sitting here. We could, yeah, let's write down these observations so that we won't forget. One thing that's I still hardly imagine, for example, building a logic board with such gates. You know that, actually, okay, jokes aside, this, I didn't make this up. I didn't make this up. These logic gates, actually, well, there is an idea for these logic gates. And you know what's really cool about this? I actually will include that in a video, which will come out now like a week or something, about information. Here's the thing, when we have logic gates, right? When you have logic gates with input A and B, right? And then output C, here's the thing. You input electric current, right? Through these. You input electric current, you get some electricity out. That's how logic gates work. But this loses energy. It always loses energy. And the easiest way to imagine that, let's imagine that, each one of those represents 1 unit of energy. Then, in this case, I know I'm having so much trouble writing an AND gate. In this case, no matter what you choose, you lose some energy. Well, over here you don't lose any energy. Over here, you input 1 unit of energy, you get no units of energy. Over here, you input 1 unit of energy, you get no units of energy, which means net loss -1, net loss -1. Over here, you input 2 units, you get 1, net loss -1. So in these gates, you lose units of energy. And that's actually what's happening inside computers. That's why computing on computers takes so much electricity, because you will lose that energy. That and obviously other funky stuff like, cooling, actually we lose that energy as heat, so that would also help with cooling. But that doesn't matter, that's not significant. And so what was proposed is these gates were actually proposed with 3 outputs, because then no energy would be lost. And if no energy is lost, that means we can, we can input some energy into our circuit and get practically the same amount out of it, but convert it so that it is different. It's because energy loss and information loss are related. So these logic gates are actually a thing. The problem is that it's not worth doing yet. It's just, we still are optimizing computers for different things, and energy is very low on the list. Because right now, if you had the option of something that takes, twice as much energy but is 4 times faster, then you will obviously choose the speed, because that's why graphic cards are the thing. I love having a computer with PSU which can output 1000 watts. So sorry, by the way, 1250. All right, which is a lot. Now, that's really interesting about an AND gate is that it is just multiplication. No, I meant to copy an equation. That was rather... Excuse me, my Discord is not... Ah! Why is my Discord like that? Alright. Whoa, if... I mean, that was one of... Oof. Can you imagine if someone was, I don't know, messaging me the bank details? That would be rather awkward. It always happens to me. Every single time I stream, someone's messaging me the bank details. It's getting annoying. Anyway, 0 times 0 is equal to 0. Big shocker there. 1 times 0 is equal to 0. Once again, 0 times 1 is equal to 0. 1 times 1 is equal to 1. And now it's time for the madness. Because... 1, by the way, I totally messed up. Now it's time for the madness, because if we want to apply this onto this, we have to change multiplication so that it would have 3 outputs. That sounds insane! Still, my best idea so far is... My best idea so far is to just use vectors. But I know that will bite me later on. Wait! Or maybe it won't. This was on stream, I think. Really? You didn't see that? Anyway. I think I might have an idea. With vectors, that could be rather smart. Maybe. What if we saved every single number as sequence of hyperoperations? If we're doing everything around hyperoperations, might as well. So for example, if B is equal to A arrow arrow C, then we could compute that B, but it would still be this. That would solve the commutativity. Well, yeah. But yes. Right? Am I insane here? Am I sane or insane? Could this solve the problem? Or maybe I didn't explain that well because half of it was happening in my head, so I should probably explain well. Okay, great. So, basically, if we have a number, for example C, which would be equal to 8 arrow B arrow arrow C down arrow D. Actually, C shouldn't be here. This C is on the left already. D down arrow F, for example. Then C, we could compute C, but it would be saved only as link of hyperoperations. That would solve a lot of problems. It still doesn't solve one problem, because it would solve a couple of problems, I would say. First of all, when it comes to our root problem, right? X squared of root is always equal to, when you're putting a real number over here, then we always get a positive number out, which is a problem because that means there's information loss. Do reals include? Well, doesn't matter. If we input -1 or 1 over here, we get 1, which means information loss, which is bad. That would solve it. That would solve it, because if we save X as a chain of hyperoperations, then this operation would actually look like this. X... so wait. X up arrow, up arrow, up arrow 2. Down arrow, down arrow, down arrow 2, and then we would just cancel these two in order to compute the x, which would work. Half of almost everyone left the stream at the moment because I don't blame them, honestly. What I'm doing here is madness. So we could. I don't think that this is actually that important. Let's just. So that means we would need to store. That means we cannot just output a simple scalar as our operation result, which means that operation result. One thing. So what can we do? I should go to sleep, but I'll keep the stream open. You don't have to. Listen, I appreciate it very much, but this stream, I'm not doing this stream for the views or anything. I'm doing it. Actually, I have no idea why I'm doing it, to be fair. I'm boredom, I guess. I have stuff to do. Procrastination. What can we do? One quick note before we move on. When we move on to the proposed solution. Hyper operations can be stored as a chain because of its lack of my goodness, I keep forgetting that. Which is weird. I've written that word 7 million times. Commutative. I'm bad at spelling commutativity. And evolution. Commutativity and evolution would suggest that lack of evolution, lack of commutativity, and phrases of evolution, lack of commutativity, and existence of evolution. No information is lost when stored as a chain. Solution. Example. 2 is equal to 1. Equation, if I may. 4 is equal to 2 up arrow 5 up actually there's 2 up arrows, up arrow is 10 up arrow 6 down arrow 8 up arrow 2. We are going from the left to right, by the way. There's no order of operations. We're going from left to right. If you want, I should have written that somewhere. We are going from left. There's no order of operations here because there's all hyper operations depending on evolution. perchance it makes any difference. That's a very make it sentence. I forgot to mention it, but in hyper-operational mathematics, there is no order of operations. Brackets still exist, but everything else is left to right. Solution. One solution, proposed solution. A solution, yeah, because that's the only one so far. One solution, one idea for how to solve this problem is to store every single number as a chain of operations until it has to be computed. That would introduce the idea of equality and identicality, which would mean that whilst 2 is equal to this, it is not identical to this. But 4 is identical to 4, and this monster on the right is identical to itself, which would restrict information loss only to computing a number and would let us treat and would let us create anti-exponents. Alright, I'll leave it for here now. It's page 9. I think we've done some pretty decent work today. I like the idea of chain operations. So you store everything as a chain until you have to compute it. When you have to compute it, then you actually compute the thing, save the number, but it's not actually identical to the original operations, it's only equal to it. So, that'll be it for this live stream. Thank you everyone so much for watching and have a great day. Bye.